All right, let's go ahead and get started. Any questions about anything before we go? Once again, I'm going to stress my encouragement for y'all to do that mastery test practice thing I put online if you haven't already done it. It's a very, very good representation of what Wednesday will actually be like. So definitely worth looking at, getting a leg up. I think the next web work is due on Thursday. And the next quiz is due Sunday. Otherwise, yeah, the mastery exam, I would throw all your weight behind that. It's 20 derivatives, all multiple choice. So yeah, if you have seen the thing on the little Unity app that the coordinator for the class posted that I sent a link to, it's just like that. Anything else? All right, so next section, chapter 4 is basically, it's called curve sketching. Basically taking all the things we've done the last 3 sections and basically putting them all together to draw basically, you should be able to draw a pretty faithful, pretty accurate hand sketch of pretty much any function I throw at you now. So let's go over some things to consider first. So, and this is by no means an ordering. Just a lot of things about functions you've been asked to consider either in this class or for several classes before. But all those things can help you sketch a graph. So the domain, how do you find the domain of a function in general, or what does that mean? All the possible x values. So let's be a little more specific. You're right, but all the x values such that what happens? They produce y values. So yeah, all the x values that actually you can input to a function and something comes out. Or all the places where, lots of ways to say it. All x for which f is defined. All right, intercepts. How do you find those? Or do I even need to be more specific about what they are? Yeah, what kind of intercepts could I have? Okay. Okay, and that was what I was going to ask next. So how do you find the y-intercepts? It's when x equals 0. How do you find the x-intercepts? When y equals 0. How many y-intercepts might I have? I can have what? I'm going to draw a set of axes over here. Think about what this would look like if I had many y-intercepts. Why can't I have many y-intercepts? It wouldn't be a function. So I'm going to say at most 1. How come I'm saying at most? Yeah, you might not have it. You might have a function who's not defined at or x equals 0. How many x-intercepts can I have? Yeah. 1 or more. Do I have to have 1? Right. Yeah. Okay. It could be infinitely many. I don't even know how to word this. Yeah, okay, that would have been good before I started erasing all the letters. But yeah, there are infinitely many possibilities, right? There could be 0, there could be 1, there could be infinitely many. Anything in between. All right, what else? Symmetry. This is something we haven't really talked about. Hopefully this has come up before, but 2 major types of symmetry. One's called even, one's called odd. Basically, and they both arise from you replacing all your x values with negative x. So even symmetry is basically, you make all the x's negative and nothing changes. You're going to get the same y values out. Odd symmetry is what happens when, or basically if you make all the inputs negative, that corresponds to the outputs becoming negative. So which one of these is which?
The first one's even, second one's odd.
How do you know the first one's even?
I just remember my reflecting over the y-axis.
Okay, is that always true?
Gradient function, isn't it?
That's what I'm asking you.
Oh, yeah.
Yeah, it's always true. And to put it back to this definition here, take any x value over here
It's the same.
and take the opposite of it, you're gonna get the same y value, right? So yeah, for the opposite of any x, you're gonna get the exact same y value. And then by elimination, this one's odd. How did they describe the symmetry to you there? Like if you're looking at a graph.
Why?
I know how it was described to me, and I always hated that description. I like to, it's if you rotate it around the origin a half turn, you're going to get the same function, right?
But isn't it reflected over the slope of 1?
No. So I mean, I think the easiest way to think of it is that an odd function is if you rotate it a half turn, it's symmetric that way, which I can't really demonstrate in a way that I can think of, but that will always be true for odd functions. Go ahead.
Would we ask to like find out if the function's odd or even just off of the function on the graph?
Yeah, do you think you could do it?
Yeah, with that.
Yeah. I mean, we'll do an example of that today. But absolutely, I mean, it's something I could ask you to do, and it's not terribly involved. What else? Periodic functions. What are the most common periodic functions we talk about or you use all the time?
Sine and cosine.
And that, yeah. So trig functions, right? Trig functions are, by definition, periodic. They have a behavior that repeats every so often. In this case, every p. Asymptotes. Where do they come from? What causes vertical asymptotes to happen?
When x is undefined.
When x is undefined. That will definitely happen. Do you remember how we define these in terms of limits? It's probably a while ago. So if you have a graph,
When the limit equals either infinity or it doesn't exist.
it has to be infinite. I mean, which is a specific way of saying it doesn't exist in a certain way, right? So a vertical asymptote looks like this, right? So you're going to have a graph act like this, or so that's one way it could act, right? What can I say about the limit at this point? We'll call it A. What is the limit as x approaches A of that function? It's infinity. But basically, that's what causes horizontal or vertical asymptotes to happen, is where you have x is approaching some point, some real number, and you have some kind of infinite limit. Could be from either side, could be from both sides. How about horizontal asymptotes then? Remind me where those things come from.
It has to be an irrational function to have one.
I don't think so. But I can think of the counterexample right now. I can, but no, it doesn't have to be irrational. Is it?
When x is approaching infinity.
Right. So let's focus on that x approaching infinity. When you're looking for horizontal asymptotes on a graph, like where on the graph are you going to be looking? Around the y-axis? Does that make sense to look around the y-axis for horizontal asymptotes? It's really more as you go far right or far left, right? Because you could have an asymptote like this, but it's really only an asymptote as x gets really far away from smaller values. So really what we're looking for is this kind of thing. The limit as x approaches positive or negative infinity of the function is equal to some number. So I highlighted this a month or two ago when we actually went through this the first time, but in terms of limits, hopefully you can see how those two things are related and why one yields vertical asymptotes and the other one is associated with horizontals. Any questions about that? I just want to stress again for horizontal asymptotes, you know, that value L up there really has nothing to do with the behavior of that function for smaller quote unquote values of X. It's really about what happens at the ends, the left end and the right end, that behavior. What else? Hopefully you can tell me exactly how to find these. So how do you find intervals of increase and decrease? Let's pick one and start with that. It's increasing if and only if what? Like what's the really, you know, telltale sign that a function's increasing?
The slope's positive.
Slope is positive. So something is positive. Where do I get my slope from? Where does that information come from? The first derivative, right? So decreasing similarly is what? What's true about the derivative there? It's negative, right? So if I want intervals of increase and decrease, you need, I mean, and I think most, if not all of you know this, you need to be looking at the derivative, the first derivative. How about local maxes and mins? How can I identify those things?
At all spots where X is 0 or where X is undefined. Yeah.
Okay, that's what I figured you meant. So f prime equals 0 or f prime doesn't exist. The local mins and maxes have to happen at places like that. Actually, like that's not clear enough. You have a local max or a local min. Does one of those have to be true?
Yes.
Okay. You have f prime equals 0 or f prime doesn't exist. Do you have to have a local min or max there?
Yes.
No, that's not true. So, yeah, give me a counter example.
Oh, yeah.
Saddle line.
Yeah, saddle points. So if I have a, you know, the x cubed is kind of the quintessential example of that. Definitely has a critical point at the origin, but I could not call that a local min or a max.
And the same thing with those like points that are points that don't exist, but also are not that local.
I would call that a local min or a local max.
I thought you said you couldn't count that as that.
No, I think I said it. I think I said there's something else I couldn't call it, but what you're describing is, I think, like, you know, the absolute value function. It has like the hard cusp there. Is that a local min, that cusp? It is. I think, Isabel, go ahead to a question.
Do saddle points count as absolute values?
What do you mean by it?
Like absolute maximum or absolute?
I'm gonna go ahead and say no, because I mean, by definition of a saddle point, it's not really changing direction. So if you have a saddle point, you're gonna have values that are larger and values that are smaller. So I don't think it can be an absolute either one. Question?
Yeah, if you have a situation where you have the absolute value function and the local minimum be also be the absolute minimum.
Yeah, and that's an example right there. And that's, I'm glad they came up. Can local minima be absolute minimum? Yeah, they can be. Must they be? And these are places where, and just this is not on the slide, but just since it came up, these things, so local extremes have to happen at these kinds of places, right? Can absolute extremes happen at these kinds of places? Can they have, must they?
No.
Where else might they be?
At endpoints.
At the endpoints. If I give you a closed interval, they might take place at the endpoints. Jarek, what I think you're remembering is last time I said that you could not call, like, so if you're looking at my absolute value function, you could not call that origin an inflection point. Okay. Because people haven't agreed on it. People haven't agreed on that, but it absolutely is a local minimum. It's the lowest point in that area. How do I find concavity? Yeah, that comes explicitly from the second derivative. If it's concave down, what's true about the second derivative?
It's negative.
It's negative. And concave up, second derivative is positive. Where do inflection points come from? What was that? They're not called critical numbers, only because by definition, critical numbers are an artifact of first derivatives. So what really am I looking for to find inflection points?
A change in the concave cavity.
Right. So one condition for that is f double prime of x has to be 0, right? And the concavity changes, because it is possible for the second derivative to be 0 somewhere, and on either side it's both positive or both negative. So any questions so far? I kind of threw a lot of conceptual refreshing things at you. But I think I have examples now. Are we good? Want to clarify anything before I make us graph a thing? All right, let's graph a thing. This one here, let's find a bunch of data and then we'll try to graph it. So I don't care what order we go in. So what do you want to do? Isabel? Okay, let's talk about domain. So this kind of function here, what would cause its domain to be missing x values? If x equals 1, why? Why is that a problem? Okay, so I have x cannot be 1. That seems legit. Anything else that we got to worry about?
Also can be negative.
Okay. How'd you both get those numbers? Okay, so I wanted to make sure. I mean, I think you can look at that and see pretty clearly that x can't equal 1. I think it's a little bit more obscure that negative 1's a value. But yeah, if you set that denominator equal to 0, you'll get x equals plus or minus 1. Those are values to stay away from. So clearly the domain cannot equal those two numbers. Anything else the domain might not include? It's a rational function, right? So what's the only way those kinds of functions are not defined is when the denominator is 0. And I think we found everything. So I'll call this, in fact, I'm not even going to give you the interval notation. This is a perfectly fine way to indicate what the domain is to say that x cannot be those two things. So we got the domain. That'll help when we graph something. What else do you want to look for?
Do the intercepts pretty easily.
You can do the intercepts. What kind of intercept do you want to do first?
Y.
All right. How do you get the y-intercept? How'd you get that?
Because the highest exponent of both is 2, and then it's just dividing both equations in there.
I don't think that's how you find y-intercepts. That's how you find something else I'm going to ask you about. What Solomon just did? That's one way to get there.
Wouldn't the y-intercept be 0?
How'd you get that?
0 divided by negative 1.
How'd you get 0 divided by negative 1?
Because if you plug in 0 for both x's, then it's
Right. So that's the real bottom line here. So let me just draw you an arbitrary graph up here. For any point on the y-axis, for any function, what's going to be true about the x value? 0. So that's the straightforward way to go after intercepts. And if you have a function that's defined in x, those are pretty easy to get because I can just plug in and evaluate. So yeah, so I know the origin is on the origin is on my graph. That's one of my intercepts. I think I got one of the x-intercepts for free. So am I done? Could there be other x-intercepts, or am I done when I found one?
No, there can be more.
Okay, so in order to find the x-intercepts, I should set y equal to 0, right? And then from there I get 0 equals 2x squared over x squared minus 1. Can I simplify that any further?
X is gonna be X equals 0.
Yeah, because, and one thing to point out is that if you have a rational function or really any fraction equal to 0, that can only be true if the numerator is equal to 0. And then from here, yes, so the only intercept I have is the origin. So aside from crossing to the origin, it's not going to cross through either axis anywhere else. So I got domain, I got intercepts. What else is worth looking at? Solomon, let's go to what you mentioned, a value of 2 for something, right?
Yeah, 2x squared divided by x squared, like the coefficients there. I remember that that's something, I thought it was y-intercept.
It's not my intercept, but it is something important that we should get our hands on.
Oh,
Asymptote.
What kind of asymptote?
Vertical. No, horizontal.
Horizontal, right? So, and really what you're looking at is, well, let me ask you this. You seem to completely ignore that -1. Why'd you do that?
Because it's whatever's the highest power, like only you don't consider those terms.
and then you look at the coefficient of those terms,
Yeah, but why can I look at those terms and ignore everything else?
because they're gonna be increasing at fastest rate.
Right. So they're gonna overwhelm that -1, right? But that only really happens for what kind of values of x? Large ones, right? Or really small ones. So that is why the horizontal asymptote comes from there. You are, I mean, whether or not you realize that you're kind of taking a limit as x goes to infinity. That's what causes the -1 to not really, you know, for its role to kind of get squashed in this. So yes, we have that limit is equal to 2, which means we have a horizontal asymptote at y equals 2. While we're doing this, we might as well look for vertical ones.
Like whatever value.
Basically, it's going to come from the domain. So you're going to have, from the domain, you're going to have vertical asymptotes at x equals -1 and 1. So I think we have a pretty good idea what this graph looks like so far, right? Also, I'm running out of room, so let's start working on it. The domain is everything except for -1 and 1, right? Where was my intercept?
X0, 0, 0.
Right, at the origin. All right, so I think I can say that about this graph so far, right? Yeah. I feel like I need more help though. So what other information can I look for? Okay, so the derivative will tell us, will give us a much better idea how we fill things in. So y prime is equal to what?
X over 2x.
Can't do 4x over 2x. What kind of,
We need quotient.
we need quotient rule. So
Bottom square.
bottom will be squared. So master test is coming up. So if quotient rule is getting away from you, I would polish that up. That's the one that's easy to remember, but also easy to mess up because it can be easily flipped around on you. So derivative of the top times the bottom minus the top. What's that? I don't believe so. The second derivative? Or second what, Isabel?
What are you writing down right now?
Should be 2x. The derivative of the 1 will vanish. All over x squared minus 1 squared. All right, so I got this derivative. Let me clean it up a little bit, but what are some things we can do with this? Oh, that was convenient. So I just found this thing. What do I want to do with it? All right, plug in values of x. Are there certain values of x you want to plug in? The derivative?
Never mind.
Okay, so we would like to plug in some values of x into the derivative, which I think is a good move, but we should probably be strategic about which ones we pick. So if I want to choose what values to pick, what's going to help me there?
Knowing what we already have.
Saying the denominator equals 0.
Right, that's usually when we start doing this test on that first derivative, we want to know where it's equal to 0, right? Or really where the critical points are. I think we can find the critical points without really setting up anything too involved. Where's that derivative going to equal 0?
0.
At 0, right? So critical point is 0, so I have other critical points.
1 and -1.
Yeah, I think this is going to be, let me put it this way. We said -1 and 1 were not in the domain, right? So it would be impossible for the derivative to be defined at places where the function is not defined. Remember, so, and again, to drive that home, remember what we said about differentiability and continuity. If a function is differentiable, is it continuous? If a function is not continuous, is it differentiable? No, it can't be. So the very fact that those points aren't even in the domain means the derivative is non-existent. So I have a derivative of 0 here, which means that what is possible for our origin? Could be a saddle point. What else might it be?
Local extreme.
Could be a local min or a local max, right? Right now, I don't think we have enough information to say that, but what other information could we get? Let's focus on that origin. How can we find out if it's a
Left and right.
left and right? So what are good points to choose?
1 and -1.
Yeah. Could you have chosen like something like -2 and 2?
No.
No. That's something I want to talk about too. So you have critical points at -1 and 1, which means if you want to learn something about what's going on at 0, you need points that are within those intervals. So what is the derivative of what is y prime when x is equal to -1/2? And again, I'll ask you this question. Do I care about what the number actually is? What do I care about?
It's positive.
So can we take some shortcuts in our derivative?
It's gonna be possible.
What's the denominator going to be? Is it going to be positive, negative?
Oh, it's gonna be positive squared.
The derivative is the denominator squared. It's positive no matter what. The numerator is just -4 times your x value, right? So what does that mean about -1/2?
Positive slope.
Positive slope here. How about 1/2?
It's gonna be negative.
Negative. Let's pick some test values on the outsides too. -2, +2. What's
Positive for -2 and negative for
yeah, positive, negative, right? So what is happening at the origin?
That's going to be increasing.
So what kind of point is that?
Max.
It's a local max. So I know how these asymptotes are going to kind of keep me, inside here. But the fact that that's a local max means I can't go above the y-axis, right? All right, so that's a big chunk of the graph. Let's think about what's happening on the left-hand side of that vertical asymptote at -1. What's the function doing over there? We just learned something that
Yeah.
is valuable.
Slope is increasing.
It's, well, not, its slope is not increasing, we don't know that. You're very close, but I'm nitpicking your word choice.
Because it's.
We don't know that the slope is increasing, we know the slope is what? It's positive, right? We know the function's increasing. And just to tell you why, I'll remind you why I'm nitpicking you. The slope is positive everywhere in, you know, on this side of this asymptote. I don't know yet that it's increasing over time. It could be doing one of these type of things, right?
Oh.
So that's why that's the distinction I'm making, because those two things are not, you don't get one for free with the other, they're separate. But I do know the function's increasing, right? Does that tell us anything about where that function has to be? Keep in mind what we know about asymptotes. Or here's another piece of data I can get for you. Let's get what y is equal, or what y is when x is equal to -2. And what y is equal to when x is equal to +2. This will be 2 times -2 squared over -2 squared minus 1, and that's equal to 8/3. And is this going to be the same number? Oh, here's one thing we didn't look at that I wanted to talk about. Does this thing have any kind of symmetry to it? So what was the test for, or yeah, how do you know it has even symmetry? Well, we don't know that yet. We haven't finished the graph, but so I don't know if we can use the graph as evidence, but what was the definition I gave you for even symmetry?
Like the y value is going to be the same on the other side, just negative.
Okay, so let's do this. Let's see what happens when I plug in all the negative x's for all the x values. What is -x squared?
Squared.
It's positive x squared, right? So I get 2x squared over x squared minus 1. So is that pretty convincing that we have an even function? I plugged in -x and I got the same function back. Which also tells us that if I figure out what's going on one side of the y-axis, I can just reflect it and get the other. So I got 2 points here. I got the value of 2 and 8/3. So that's about here. So remember, one of the ways we think about asymptotes is they're a line that your graph can approach and not reach, right? So hopefully this point makes it clear that where your graph exists. Also, we know that our graph is doing what over here? Is it increasing or decreasing? It's decreasing. So I believe it's going to look something like this. And through symmetry and the fact that I know the function's increasing over here, it's going to do something like that. And pretend I didn't cross the asymptote, I didn't mean to. So let me pause and take questions, because we did a lot of stuff to arrive at this hand-drawn function here. So we found the domain. We found the intercept. We only found one. Found 3 different asymptotes. Figured out where the function was increasing, decreasing, not defined, stationary, or critical points. And probably could do something with concavity, but I don't think we needed it to get this graph. I think probably happy with the way it is. Any question about anything we did or why any of the conclusions that we made.
Could you just briefly, earlier you explained the difference between like it was increasing and its slope was increasing?
Yeah.
Could you just briefly touch on that again?
Sure. So, and really the gulf comes between these two things, f prime of x being positive and f prime of x increasing. Is it possible for exactly one of those to be true? So I'll give you an example here. There are examples on this graph that we can talk about, but let me just graph the standard parabola for you. Parabola is a function that is concave up everywhere. So f prime is increasing everywhere. But is f prime positive everywhere? No. So another example of the fact these two things are, one does not imply the other at all. If I draw tangents going left to right here, all those tangents are going to get more and more positive as I go from left to right. So f prime is always increasing there. But clearly everywhere to the left of the y-axis, f prime is negative. Okay, thanks. A good question. That's a really important and really subtle thing. Is there something I could say that's equivalent to this idea here?
Yes,
What's that?
f double prime is positive.
F double prime is positive. And really, and just to remind you all what a derivative says, a derivative tells you the rate of change of the function that whose derivative it is. So I need to say that again. That felt clumsy. All derivative does is tell you it tells you the rate of change of the underlying function you started with. And so if f double prime is the derivative, what function is it talking about? F prime. So if f double prime is positive, that means the underlying function is increasing, which is this thing. Just like, and there's no, this is not a coincidence, this is how derivatives are. If f prime is positive, what does that mean about some other function?
F is increasing.
F is increasing, right? Which clearly that's what's going on there. And I think now from the way we've drawn this graph, can we say if it's concave up over here?
What is?
Sure.
Yeah.
It is. I mean, that's another thing we know about asymptotes. This is going to get steeper the closer I get to it. And by opposite reasoning here, this is going to get more shallow.
So on the right hand side there, the f double prime is, so it's concave up on the right side as well.
It is. And then let's talk about it. It's worth talking about. So on the left hand side, would you say that f prime is always positive? F single prime?
Yes.
Yes, it is. And it's very shallow here, but it's positive, I'll promise you. I drew it like it was horizontal, but it's not supposed to be. So the slope is always positive on the left hand side, right?
Yes.
Is the slope increasing as I go from left to right?
Yes.
Okay, so f prime is positive and f double prime is positive. Over here, is f prime positive for the whole time? Is it negative somewhere?
Oh, okay, so the slope is going down.
So it's negative somewhere, right?
Yeah.
Is it negative everywhere? It should be, right?
Yeah.
So, and I'll explain it a couple different ways. Symmetry. So if this slope is always positive, you flip it over the axis, it better be always negative. So that's one way to justify to yourself that over here, f prime is always negative. Okay, so we've said about f prime. What's true about f double prime over here?
It's positive
Why?
because it's increasing. Or, sorry, it's not increasing, but it is
What's increasing?
f prime.
That is true. So clearly this is a very negative slope, right? As I move over here, I get
Less and
less negative. These slopes are going to be flattening out. They're always going to be negative, but they're always going to be It's weird, it might be weird to think about it as the slope is increasing because they're flattening, but they're going from very negative to less negative. Is that? It's not gonna click all at once. I mean, there's a lot of different things we're doing, and you're probably gonna grab a little bit more each time. But yeah, it's tough. Of course, question.
What else does this graph have symmetry?
What kind of symmetry does it have?
Yeah, how do we know that it has symmetry?
So a couple different ways. At least two different ways. One way comes from the graph, and one comes from the algebra. So even symmetry, algebraically speaking, is where you replace all your inputs with their opposites. So replace all your x's with negative x's and see what comes out. So in this case, we replaced all of our x's with negative x's, and we got where we started, right? So that's the algebraic way to see do we have even symmetry, but also from the graph. Graphically speaking, how does even symmetry show itself?
It's a mirror image across the y-axis.
It's a mirror image across the y-axis. And really, the fact that I found even symmetry here helps me finish drawing this graph. But both of those are ways to see that a graph is even. Also, why do we think it's called even? Well, how do we usually use that word, Isabel? Yeah. That's why it has that name. So what are all the powers of x in our expression here? Or two of them are squared. What's the other power of x that's a little more hidden? 0. Those are all even numbers. So that is why that kind of symmetry has that name. So let's see how we did. Looks pretty close, right? Except theirs is a lot better. But yeah, I mean, found all the data we needed. And yeah, got the asymptote. I mean, they don't mark their asymptotes or anything, but we're good. Any questions about any of that process? So I probably don't have time to finish, but we'll get going here. I want to find all the information we need to sketch this guy. So you tell me where to start. Domain? What's the domain here? What? Is it all real numbers? Let's think about it. So we kind of have two functions multiplied together, right? Is x ever undefined? That's a polynomial. It's a simple, this is polynomial, so it's always defined. How about e to the x? That's what. Yeah, you can raise e to any power. You can raise any number to any power. So that is fine. So this domain is all real numbers. Are we going to have intercepts? So we can look for a y-intercept, right? Y equals 0 times e to the 0, which is 0. So I have an origin again. What happens if I look for x-intercepts? 0 equals x e to the x. Is it only going to be 0? So I have two things multiplied together equals 0, right? So from there, I can kind of boil this down into x equals 0 and e to the x equals 0. One of those is, yeah, fine, but we didn't learn anything new. E to the x equals 0, is that ever going to be, how do you solve that? If you take a natural log of both sides, I get x equals the natural log of 0. What's that? That is nonsense. So yeah, the only intercept we have is the origin. Okay, we got domain, we got our single intercept again. What else? So here's the thing, there's so such thing as too soon. I mean, we could have done that first. So, I mean, there's no prescribed order to do any of this stuff in. So, yeah, let's find it. What's y prime? I'm going to pay for my parking while you're all thinking about it. Oh, no, I'm not. What do we need to find the derivative? Product rule and
Just keep product.
you probably get away without chain rule.
Because derivative of e to the x, you get an x.
Right. So I would call this derivative e to the x. So derivative of x times e to the x
Yeah.
plus x times the derivative of e to the x. So we agree with that derivative? All right, now that I have it, what would you like to use it for?
Points for max.
Yeah, let's find critical points. So if I set that equal to 0, how can I solve that?
You divide the x out of both sides.
The x is not common to them. But what is? What's that, Isabel? Yeah, I can factor out e to the x. And one thing I want to caution you about is, Solomon, I'm not sure if you took this back immediately after I said it, but you said for a moment dividing by e to the x. If you divide by things that are variable, you might lose solutions. Also, if you divide by things that might equal 0, that's a huge illegal, that will not work out for you. But I can factor it out and see what happens. So I get e to the x times 1 plus x equals 0. Does that tell us anything about critical points?
-1 and 0.
-1 and 0? I don't think I agree with 0.
Isn't that? As long as it-
What's e to the 0?
Oh, no, yeah, it's not.
E to the 0 is defined. It's 1.
Just one.
So, and I'll remind you to one of these upper lines here. We tried to set e to the x equals 0 and solve for it, and we didn't find anything, right? So our only critical number is -1. Well, our only place where the derivative is equal to 0 is -1. Is that derivative going to be undefined somewhere? What's that? Well, that just proved it's never undefined, right?
We can't have something that's undefined for matching.
You can in general, but how about this? Yeah, absolutely. In general, local mins and maxes can come from the derivatives, fails to exist. But what I'm asking here, do we going to have any critical points like that to worry about? I think the rationale I get here is you have a polynomial times e to the x, which is always continuous. I still have that. So that's always going to be continuous, which means it's always defined. So that's the only critical point I have. Let's make one more little dent in this before we go. So I know that I have a single critical point at x equals -1. What can that teach me? Yeah, we can find asymptotes.
Also look at increasing, decreasing that side.
Yeah, let's do asymptotes next time. Let's do increase and decrease because we just found the derivative. So I can find that from looking at the first derivative. What point should I try?
-1.5 and then 1/2. Or you can go -2.
Yeah, don't choose fractions unless you were stuck with them. -2, what's a good other point?
0.
Yeah, always choose 0 if you can help it. So another derivative is 0 here. What is f prime of -2? It's e to the -2 times -1, right? Is that positive or negative?
It's going to be positive. -e is -2.
That's negative. Is e to the -2 itself positive or negative? And that's something easy thing to get tripped up on. Just, yeah, think about this. If you raise a positive number to a power, is it possible for a negative to come out? All right, so that's positive. What about f prime of 0? E to the 0 times 1 plus 0, which is? It's 1, which is positive. So what kind of point have you found?
Absolute min.
Maybe not.
Sorry, a local min.
Yeah, local min. It probably will be an absolute min. We got to find that out. So local min at -1, -1 over E. Oh, I gotta let you go. So let's stop there. We'll keep plugging away at this on not Wednesday, but Friday.